In the name of Allah, the Compassionate and the Merciful. Hello guys. In this video, we are going to have a concrete section ductility ratio optimization with continuous variables in C++ programming. As you see at the left side of this picture, you see that this concrete section with different layers of steel rebar, strain relation, stress relation of steel and concrete. So concrete relation is defined by Whitney stress block, and for defining the steel rebar relation as a stress and strain relation, we use this formula. So we are going to solve the moment equations for catching the moment curvature analysis. As you see in this example, we catch the 3-point, the ultimate moment, the yield moment, and cracked moment in here. So actually we have 3 points for calculating the of our moment curvature analysis, and actually in this example we have 6 layers of steel rebar with different distance, and at first we guess the initial steel rebar area, and with Newton-Raphson method we are going to solve the best solution of catching the moment curvature analysis, actually the optimum and minimum one, and as you see in here, I defined the minimum and maximum section ductility ratio. It is lower bound and upper bound of our modeling. So if we want to minimize it, so we are going to catch and solve the optimum solution for catching this value. And let's see our input file, and as you see in this file, actual forces, width of concrete section, height of concrete section, lower bound minimum section ductility ratio, upper bound maximum ductility ratio, FSC, ultimate concrete strain, yield stress of steel rebar, ultimate stress of steel rebar, module of elasticity of steel rebar, strain hardening, ultimate strain of steel rebar, and number of iterations, and this formula and iterations for solving the equation of our model in ultimate moment calculation, and this iteration and this converge value for solving our optimal solution, as you see. And these values, as you see, the summation is 1 because our distribution of each 6 layers must be equal to 1. Okay, and let's see, the distance of each layer is shown and defined in here. So let's see our programming in C++. I model it in C++ programming. As you see, all data imported from here, and then shows in here. You see that, and it checks for error if it is available or not, and analysis started from here. So you see that at first we guess the all steel rebar area equals to 10% of the area of the concrete section, and the distribution coefficient, as you see, which I described in here, it is for our initial value optimization. You see that in here. So we're going to calculate the cracked moment, yield moment, and you see that in here ultimate moment. So you see that it is for each 6 layers. So in here, so you see that in here. Yes, and after calculating the initial value, we're going to find the optimum solution and optimum steel rebar area of our concrete section for catching the optimum and minimum ductility ratio of our model. You see that I use while and the process is going to be calculated, and in here yield moment and ultimate moment is calculated too, and you see that in here if we find the section ductility ratio which is between our lower bound and higher bound, between the minimum and maximum ductility ratio, so the optimum solution is found, and then the analysis is stopped. So, and at last we're going to output our data in text file. You see that. So in here I have an Excel file of this modeling which I wrote it and compile it in C++. You see that in here all data it is shown input data and analysis report. It is for our initial analysis of moment curvature, and with the initial value you see that with initial value of steel rebar area, yield moment, yield curvature, ultimate curvature, and section ductility ratio all is calculated, even and overstrain factor is calculated too. And then after iterations we found the best solution of this steel rebar area, each in 6 variables. You see that we found that the minimum ductility ratio of 50, you see that, which I defined in here for our lower bound. You see that in here, and you see that it is in here. So we found the best solution with iterations. We catch the best optimum steel rebar area. So thanks a lot, guys. I'd be glad to know your opinion about modeling of this concrete section, actually the optimum optimization solution. And bye.